Hello, ladies and gentlemen, and thank you for standing by. Welcome to this ASM webinar, Nodular Gray and CGI Iron and Image Analysis Perspective. I'm Joanne Miller, Senior Editor with ASM International, and we're glad you could join us. Today's presentation is part of the ASM webinar series designed to provide information you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. The series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsor of today's webinar is Clemex Technologies. Since 1990, Clemex has been at the forefront of high-end image analysis, developing solutions for the characterization and analysis of microstructures. In recent years, emphasis has been placed on machine learning algorithms, enabling their customers to go beyond the limits of traditional imaging methods. Clemex specializes in the integration of advanced computer vision, building out tailor-made software-hardware solutions that best suit their clients' needs. They exclusively use leading brands of microscopes, stages, and cameras in order to uphold their unwavering commitment to delivering high-quality results. We're proud to have Clemex Technologies on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the GoToWebinar session, dial 877-582-7011. All participants will be in a listen-only mode during the presentation. Feel free to submit written questions at any time by using the Q&A window located in the upper right corner of your screen. Click the question mark button to open the Q&A window, type your question in the box at the bottom, and click the send button. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is ASM's flagship technical magazine. It provides information about leading-edge developments and trends in engineering materials and the methods used to select, process, fabricate, test, and characterize them. The magazine also covers emerging technologies such as nanotechnology and additive manufacturing, as well as management topics of interest to scientists and engineers. With that, I'd like to introduce the instructor of today's webinar, Marc Lavallee. Marc Lavallee has a metallurgical degree from Trois-Rivières, Quebec, Canada. He worked as a metallurgist in both an aluminum foundry and a cast iron foundry. He also worked at Buehler for 13 years as a sales engineer for sample preparation equipment. Marc has been at Clemex since 1997 as a business development manager, initially distributing sample preparation equipment in Canada. His sales involved not only sample preparation equipment, but also method development for his customers. Eventually, his sales role became focused on image analysis products and Clemex core products with a worldwide reach. Marc has developed deep knowledge in image analysis at Clemex for multiple industrial applications over his 23 years with the company. He has worked in various fields of interest, including metallurgy for applications like grain size, layer thickness, and inclusion rating, aerospace, automotive, and medical devices for cleanliness applications, pharmaceutical applications on particle size, as well as electronic applications. It is a pleasure for me to introduce Marc.
Well, thank you very much, Joanne and Kelly, for having us on board. I want to thank ASM for allowing us to present this. And also, everybody, thank you for joining us. And also, I want to thank my friend Rod Benz, who's been following us as well. So what we're going to talk today is nodular gray and CGI iron, compact graphite iron. How do we look at them from an image analysis perspective? So we'll have a quick overview. We'll look at the history of Clemex. What is cast iron? What is it used for? The standards that we used in image analysis to validate the graphite, mainly the graphite, and also gray cast iron, and also how do we measure nodules and CGI with image analysis. So Clemex was founded about 30 years ago by some creative people that were interested by image analysis, and they developed Vision PE, which is our flagship software. And over the years, integration of harness, well, not harness tester, well, as well harness tester, but microscopes and all the hardware that is required for a complete system to work. Here are some applications that Clemex is involved in. You can see that we have, hold on, I'm just going to put this here. Aluminum, inclusion rating, some other aluminum, some grain size that we've seen. And also some non-metallic, foam, composite. This is an old TV set, but it's just to show we can measure an object within an object. Life science, if we need to do that, we're mainly materials, but it's also possible. And this is what a system look like. Normally we have a microscope, camera, motorized stage here, control, and the software controls everything. So we can integrate the software along with pretty much all brand of microscope, but we're working mainly with Nikon and Leica because we can use their motorized microscope to improve the overall use of the system. We can import images from other software, SCM and the likes. Image change, there we go. What is cast iron? You know, cast iron, that's just a generic name for an iron alloy that is between 2 and 4% of carbon. So when it's below 2, it's called steel. And above 4, it's not used very often, but it's just a big carbide piece of metal. The production cost is lower because the temperature, the melting temperature is lower. So you will see that in a moment. And we use the term cast in cast iron generally because that's all we can do with it, in the sense that it's cast and then it cannot be drawn, flexed, or bent or something like this. It's it's too brittle. So generally, a piece will be cast and then machined. So that's normally the use of this word that is normally related to cast iron, and you will see that it's generally used. Now it can be called with other names: flake graphite, gray iron, spheroidal graphite iron for ductile, and CGI, as I said. I don't think there's any other name for this. There are others. It's called white cast iron, but this one has no graphite in it, so it's only carbides. So that's why when you break it, it's white. So the mechanical properties of the cast iron is due to the shape and size of the graphite, along with the microstructure, of course. But this is what we're going to verify today, or that we can see that what you can do with image analysis to verify those graphite information. Sorry, the image is not moving right away. So this is the good old phase diagram, iron carbon. So basically we have the carbon at the bottom here, and then we can see that this part here, 2%, there's a line, and to the left of that we have the steels, but you can see that's the melting temperature is quite higher than what we have here for the cast iron, which is between 2 and 4 generally. So when the carbon is there between 2 and 4 and you have enough silicon in it, so the graphite is generated, and the cost to produce it is lower because of the temperature being lower. The way gray iron is produced is normally we're using a pig iron. It's like just iron, basically, without carbon. And then it's mixed with scrap and some ferroalloys, ferrocarbon mainly, and also with a slow cooling rate. So when you have that, you end up with a gray iron. And so where the graphite, like here, those flakes here, are being generated. So generally the properties with this is fairly low, fairly weak in a sense compared to the other material. So low tensile and yield strength, almost no yield strength actually, because it's so brittle. Very low ductility. But the benefit is that because of that graphite is it's quite good to be used in machining. You know, when you're machining it, the graphite is acting as a lubricant. Ductile iron is produced using molten gray iron. And so the idea is that you make a magnesium treatment to it to generate or to turn the gray flakes into nodules. So we'll see that a bit later on. Now the benefit of ductile iron is that you have a much higher tensile and yield strength. We have something here and a good ductility, hence the ductile iron. So sometimes like one application is for camshafts, for example, where the wear, you know, of the cam is there, but also the flex because it's not too rigid. It can flex a bit, and enough so when you're pressing on the pedal and the cam is turning, the torque will not shatter the shaft there. And compact graphite iron, I'm not sure if it's a lot of people are familiar here. It's more popular in Europe, but it's the same principle as with the ductile iron, but it's just using a smaller magnesium quantity for the treatment. So probably the ductile iron, the CGI was developed with the bad ductile iron, and I said, oh, this is something different here. Now the benefit here is that why would you bother doing some weaker ductile iron? The benefit here is that it has a good heat properties. So it's a good heat transfer, and it's used for things like exhaust manifolds and then cylinder blocks instead of gray cast iron because it has better properties than gray iron. Just so the metal can be thinner, so the walls are thinner, so it's a weight improvement. So this is how the nodular iron is made. So that's the magnesium treatment. So sometimes most of the small foundries would do something like this, where you put something at the bottom and then you pour the molten iron over it, and then makes a flash, and then it's an exothermic reaction, and then some inoculants are added as well to help with the generation of the nodules. And so that's one way. There's like two other ways here. Like this one here is similar, but the difference is that there would be a cover on here to slow down the reaction so that it would wait until this melts down. So maybe it's until it's half full, and then start happening. Or the best way, or I guess the most professional way for large production, is using a Thunder's ladle, where you have like a big bucket on the top here where you pour the cast iron, and then this flow here is continue. So that's normally you have to have a certain flow to make the heat treatment, not the heat treatment, but the magnesium treatment to be efficient. So we'll look at those standards. A247, I'm pretty sure everybody's familiar with that. ISO 945, which is the same thing, it's just the European pendant of the A247. We'll look at 2567 for ductile iron, so you will see that in a moment. It's the percentage of nodule within the surface. And 1612, it's the pendant of this, but for CGI, or graphite compact iron. So in A247, you will see that in the report why it's called like this, but I want to point out that's where it's coming from. So normally the value that we would see in the report would be something like this. So if you have gray iron, it would be labeled at 7. So 7 would show this part here. So at the bottom here it says type 7. All right, so we have some flakes. Then A would be the other class, so it would be like this type here. So if it would be a bad one, it could be like the D version. So you could have a good section of this, and a weaker section of that. And it's the same thing for nodular iron. So for nodular iron, normally would say it's one of those ones, right? And then we're not going to mention this part generally, unless we have a lot of this. Normally, if we don't have like the right percentage of nodule, that means that the heat treatment or the magnesium treatment didn't work so well. So part of it is not transferred. And the number at the end is related to the size of the flakes or nodules. Now these are the type of nodules that you could see. So that's normally what you see most, the 1 and 2. That's normally what we see mainly in the when the treatment is correct. Every now and then we get some of this, but it's more for malleable. This one here happens also, as we saw that this is similar to the CGI. So when we get this into a nodular iron, that means that the treatment didn't work too well enough. But if we're doing CGI, that's what we're looking for. And so these two here end up sometimes mixed with the two main ones, so 5 and 7. So generally 80% of nodular graphite shape 1 and 2 is what is required into the as a result in the nodule count. So when we're doing an 8247 method, or 945 for that matter, it's the same thing. You will see the difference shortly. So the idea is that we want to make it as automatic as possible. So the sample is placed on the microscope, then you click start, and then the system will measure, when you have a motorized stage, will measure, let's say 10 fields. And then it could either be 10 fields, or you could say a conditional instruction can be set to measure a certain number of round nodules. So the standard says you need to have 400 nodules, good nodules, not just any nodules, but good nodules. So the software will count those, and then when you have 400, it will stop. And then when it stops, if you need to go further and to reveal to etch it for the pearlite and ferrite, so there will be a pause. So you take the sample, etch it, put it back on. So once it's etched, you click OK again. So when you click OK, it will load another method, and then the pearlite ferrite will be measured over the same number of fields, which is important, because if you do 10 fields of the first one and 3 of the second one, I mean, you're not covering the same area and also the same variation. And lastly, if you need to measure the carbides, it's possible. Then it would be a third pause, and then you just take your sample, etch it with this ammonium persulfate to blacken the surface, and then all of the carbides will come out white. And then you just run the sample again, and then when you're done, right? So at this point, all you have to do is click OK and take your sample back and forth to etch it and all. So you end up with this result. Sorry. So normally it's done at 100x, and this is our graphite percentage, graphite, perlite, and ferrite. And we get our nodularity by count, by area. That's normally what we're looking for, 80.38. And then we have some data on the side here. Well, actually, here we have this the classification for the distribution. And here we have our the density, number of nodules per square millimeters. And that's all the graphite per square millimeters, and the other type per square millimeters. All of this is calculated automatically. And you have some typical images here. Now, just to show you the difference with ISO 945, it's exactly the same principle. The difference is that if I just go back here, what is graphite 1 here and graphite 7 here in 247? It's the opposite. So what they call 1 is 7, and what we call 7 is 1. So it's just inverted. Yeah, so the difference here again, and then there's also the class, which is a little different, like the class size, but overall it's the same principle. Now at the bottom here, we see we had the add to summary file. So once you've done, when you click add to summary file, you end up with this here, and then you can accumulate the data So you don't have to export it and extract the value. This will be exported directly into an Excel sheet, and the data will be kept. And then if you have a macro that you can retrieve this information, you can do that. Now, just to show the idea of a production system, so we had a customer that what they did is that they put the microscope, TV, monitor, everything in a clean area, and then the monitor was facing the window, and the user had a small access with their hand to put the sample on the microscope, and they could click with the mouse to start the analysis or enter the information from the outside, from the plant. So so they basically just click, put the sample, click, and then it was done as I explained before, and it was in a clean environment. So it was a good system, and the system would remain clean for much longer. Now for flakes, it's somewhat similar, but a little different in the sense that you need to have some manual intervention. So the first part is to measure the flakes to the flake size. So let's say that we have our flakes here, right? So the system would look at all the flakes that you have over 10 fields, and then it would measure all the first part of the flake size. And then on the second part, again, you put the sample, you just have to click next for the next one. And then once it's ready, you would look at the image and it would go around the B, you know, it says B graphite. So you found the one that have rosette like this, and then you just circle them. And once you're done, you click on OK, and then the C graphite, you know, one with the oversize. And then the D and E are together. Sorry. So D and E are together. So once you're done, you end up with this. You could also do the perlite ferrite here. So this is what the reports look like. So again, all you need to do is just put your sample on, have the measure the flakes, and then you circle the area that are representative of the different types. So, and it will make the calculation. Again, in 945, it's similar. It's just that the range is a little different, and also the how we where is it? Like whatever is A, B, C is just inverted. Now there's another standard also that was made for image analysis. It's the IDs to measure percent nodularity, and the idea is that we need to identify what is the nodule, and what it do is that we define the roundness of the nodule. So with this formula here, and then so we say whatever is above 0.6 and up. So 1 is totally round, 1 would be flat, let's say. And 0.6 would be like round enough to be considered a nodule. And then it would put that in the formula where it would just make the count of the number of nodules per area. And here we have a distribution of the size as well, right? So, and we end up with this report. So this is exactly for image analysis. This one here is 16112, is made for CGI, compact graphite iron. And so you can see that we're using the similar formula. So, but the difference is that the calculation is slightly different because we're counting the nodules, the area of all the nodules. And we can see here that the nodules are 0.6 to 1. So it's similar to the other one as far as roundness factor. And then we have this intermediate one, which is represent this guy here. And then the compact, the one that are longer. So those are the pink one, right? So the intermediate are green, and the red are the nodule type. So the calculation is made using that formula. So we end up with a percent nodularity, and normally they're shooting for about 20% or less. They don't want it to be nodular because these flakes are kind of straight, right? And the reason why we're using that 0.5 is because the one that are intermediary, like the green ones, could be they could only be in the different plane. So they're calculating that there's a potential for the one that are not nodule but not flakes either, that it could be just in a different plane, and it's like the head of a bone protruding out of the ground. So that's why the 0.5 is limiting the impact of the intermediate. Here's a custom application that I did for a customer where the idea was to look at the compact gray iron, but they were interested to find out about the flakes that were remaining. So the idea was to look at how we qualify the CGI flakes, and then we exclude all the ones that are flake-like, that are long or bigger, or because normally these would be a certain length, like chubby a bit, and then round at the edge. So that would be the definition of compact graphite flakes. And then you can see the ones that are long here are isolated. So the idea actually was quite a benefit for them, because before they used to sit down in front of pictures and draw all of those manually. So this is done automatically now. We're getting close to the end. So this is a stage micrometer that we use for calibration. We can use it for automatic calibration. So basically, the software look at the rectangle here, and there's a barcode. It identify the barcodes here, and then we'll look at the measurement. So each rectangle has a nominal value, and the calibrated value would be here. So that's the value that was certified along with the micrometer, and then we have a traceable information. So this can be used with a manual microscope or a motorized microscope. And so in conclusion, we can adapt to any standard, pretty much. The detection compared to a manual is not guessed. It's really when you're looking at D and B type of class, everything is done more automatic because you have a better evaluation. You can see it, can draw around it, and it's more efficient. We can do multiple measurement into a single pass. So for example, we can have like in the nodules, we could look at the nodules the way they are. We could also look at measuring the roundness of other factors that are in it, and all in the single pass. Like you saw there, we can chain multiple routines together. So when you start with the measuring the nodules, and then the user doesn't have to ask or request another routine. It will just load it automatically to do the pearlite, ferrite, or the carbides. All the conditions of analysis can be recalled. So that's quite interesting in the sense that it's easier for us to have repeatable analysis when everything is working the same way all the time. Motorized microscope, that's all together. So we can control the microscope. You saw that we can export report. And then we can do all kinds of other applications like banding, grain size, inclusions. And thank you very much. And if you want to, I'll ask Joanne to take over. And thank you very much for attending the seminar. If you have any question, go ahead, if we have time.
Thank you for that excellent presentation. Before we conclude, I think we do have time for just one or two questions from our participants. So one attendee wants to know, we need to modify the standard to adapt our product. Are we allowed to do this?
Yes, that question comes up pretty often. Normally, the standard is there to be as a guideline, right? So that everybody works the same way. But if there's an agreement between the customer and the supplier, you can modify it. We see that pretty often in various standards, like in cleanliness, for example. People will say, I don't want this group of particle size. I want it to be wider or narrower because this reflects our production. So there's no problem to do that, and the software will adapt to any modification that you need to do.
Okay, that's good to know. I think we can take one more. So another attendee says, our personnel is evolving all the time, where the users are not the metallographers anymore. So is there a way to make the knowledge transfer easy?
Well, what I was talking earlier about the microscope, being motorized is the best way of doing this, because if you have a motorized microscope that you can control the illumination, the diaphragm, everything that could affect your threshold, and the threshold is then, once the microscope is all automatic and the settings are repeatable, the threshold remains the same. So if you have something that has a darker edge or that lighter edge, we have another exposure that can take care of that. And so if you have a new person coming into the lab to work with it, training is minimum. Just show them how to put the sample and click start, pretty much. So it's quite easy.
Good,
Yeah.
thank you, Mark. Unfortunately, we don't have time to answer all of the questions we received, but in a few days, all participants will receive an email with further contact information. I encourage you to complete the brief survey that will appear on your screen as you exit the webinar. With your input, we can continue to provide webinars with high-quality practical information that you can use. I also encourage you to follow up with Mark for more information about nodular, gray, and CGI iron image analysis. Again, I'd like to acknowledge the sponsor of today's webinar, Climex Technologies. With their unwavering commitment to delivering high-quality results, Climex Technologies builds tailor-made solutions that best suits their clients' needs. For more information, visit climex.com. Thank you again for participating in this ASM webinar. Have a great day, everybody.